Say that earlier example of rigid body may not be covered in the video here because the timing is almost 33. You can make out that fine. Example number 5. You have come across this. What is called as say a particle or a body is thrown in a vertical axis. Say a body is thrown vertically upward. When a body is moving in a vertically upward direction or in a downward direction, we have studied this motion along a straight line in PU first year. That is S is equal to ut plus half at square. So if a particle or a body is thrown in a vertically upward direction along a straight line and body is moving with some initial velocity u. This is its initial velocity. It's a simple example but interesting one. Can we upgrade, can we apply what we know to this classical mechanics? We have studied Newton's laws and motion along a straight line or a simple motion, circular motion. Already we have taken that. This is again a known example for us. What is a body is moving along a straight line. It may be moving along x-axis, moving along y-axis or a z-axis. It is moving along a straight line, vertically upward or vertically downward. When I throw a ball, a cricket ball, in upward direction, exactly in upward direction, if you throw with some angle, this will become a projectile. It is a two-dimensional. Here, this is an example of one-dimensional. We call it as one-dimensional motion. One-dimensional, fine. One-dimensional motion. In this, a particle is thrown vertically upward along a straight line. It's perfectly thrown in a perfectly straight line with some initial velocity. Look at this problem. Here, this velocity doesn't have any component along x-axis. X is 0. This velocity doesn't have any component along z-axis. Okay, z is 0 and y is equal to, I'll write here ut minus, because it is moving against the gravitational field, ut minus half g is the acceleration due to gravity, gt square. What is the constraint here? Body is allowed to move. Body is allowed to move along a straight line, that is in a vertical direction. It's one-dimensional motion. One-dimensional motion. Time is changing. Time is varying. So, can we fit this equation? We are going to call this as equation of constraint. What is the constraint here? Body is thrown vertically upward along a straight line. That means we can write its equation, and this is the simplest equation, and we all know this very well. Ut plus half gt square. G is a constant at a given place. T is the time which is varying. T is the time which is varying. U is the initial velocity with which we are throwing the object in upward direction. U is the initial velocity certain times. If U is 0, initial velocity is 0, we take it as 0 and then we write this. This is. Similarly, you can develop the example for a constrained motion or called as holonomic motion for a two-dimensional. Can we write the equation of a constraint if a body is moving in a projectile path, projectile motion? Can we write? Yes, whatever the equation of motion you are writing, That is the equation of the constraint, you can say, and the constraint writes the equation here. So we have removed this. We don't require these two. Only one parameter we require, one coordinate we require. T is time varying. We have written general equation. Hope you remember this or go back and see this. F of I, x1, y1, z1, x2, y2, z2, x3, y3, z3, and so on up to xn, yn, zn, t, which is equal to 0. This is general equation of holonomic constraint. So this is an example. Earlier example, in case of rigid body, say the t doesn't arrive, t doesn't come into picture because the distance between any two particles is always constant. Here in this example, t is varying, t varies, time is varying, but the motion along a straight line, that is its constraint, one dimensional, we have written the equation, and this is a good example to understand what is a constraint and what are the holonomic constraints. Well, we'll go for another example, that is example number 6, I think so, that is double pendulum example. I'll draw the picture here, double pendulum, say this is fixed point, here is, say this is O, and here is some mass attached to this inextensible rod, a light rod or a string. I'll call this as particle 1. To this particle we have attached another mass. This is called as double pendulum. Look, this is, we have discussed simple pendulum where we require only one coordinate, and here we have taken the double pendulum. This is, okay, double pendulum, theta 2. Now, say this is M2 or second particle. So two particles are connected. In case of double pendulum, I'll write here double pendulum is an example of holonomic constraint. Well, we have discussed simple pendulum wherein only one mass is attached to the string or thread. Right, here you can say these are the two rods, they are light, inextensible, they cannot be expanded with weight here or the mass here, they are light, maybe thread. Okay, the other one, M1 and M2 are the two masses. This is M1, you can say, this is M2, or two bodies. This is two body problem called as double pendulum. In case of simple pendulum, we have concluded only one coordinate is enough, because this distance, say, earlier we called it as L, now we will call this as L1 and we will call this as L2. This L2 is same from this point or from this point. Either you can take L2 as this from the point of suspension or from the particle 1 and same. L1, the distance between the two, that is point of suspension and point mass, M1 is same. Point of suspension, that is from distance between the two, that is particle 1 and particle 2, is constant here. This is constraint 1, this is constraint 2. So here, in case of double pendulum also, we need in our 4 coordinates. That is, you can say R1, theta 1, as in case of simple pendulum, we need R and theta for one particle, and R2 and theta 2 for the other particle. So this R1 is equal to L1 and R2 is equal to L2. And these two, that is R1 and R2, are the coordinates here, and these two coordinates remains constant. They doesn't vary. They are independent, and say we have eliminated them from the equation. So you can say here only two coordinates q1 is equal to theta 1, q2 is equal to theta 2. Theta 1 and theta 2 are the two coordinates we require. And these are the two coordinates we require to describe the motion of here a double pendulum. There are numerous examples. You can go through the different books. They will specify the different examples. You have to try them, solve them, and get your doubts clarified. Okay. Only two coordinates are enough to describe the motion of this, and degrees of freedom here in this case for a double pendulum are equal to. Now, in all these 5 or 6 examples, what I have written at the end, Q1, Q2. Now I will come to this point. What is called as Q1, Q2? See, sometimes we are going to introduce this concept. We are going to learn about this Q1, Q2, Q3 and so on. See, this Q1, Q2, in one case we got only one, in other case we got two. We have not gone for an example where 3 parameters are required, 3 independent coordinates are required. We may come across that also. So this Q1, Q2 happens to be the degrees of freedom. These are independent coordinates required to specify the configuration of the system, and they are called as degrees of freedom. Further, we are going to call them as generalized coordinates. Generalized coordinates. In my introductory class on classical mechanics, somewhere I have touched this, somewhere I have spelled this. That's saying the classical mechanics, and say the part of classical mechanics and its development can be used to generalize general theory of relativity and quantum mechanics. Now this is the point you can remember. They are called as generalized coordinates, and we are going to discuss this article, generalized coordinates, in detail. We are going to write the equation of motion of a system. Equation of motion of a system, maybe a simple pendulum, maybe Atwood's machine, maybe Newton's second law, F is equal to m into A. We can write them using the generalized coordinates, what is called as Lagrangian formulation. Here afterwards, we may move on to what is called as D'Albert's principle. We are going to learn it. What is called as virtual displacement, we are going to learn it. Virtual work, we are going to learn about it. And then generalized coordinates. The important article of your syllabus is generalized coordinate. Using generalized coordinate, we are going to derive Lagrangian equation known as equation of motion. Once we write Lagrangian equation, you can apply that equation to any one of these mechanical problems. Okay, so I want to pass on to non-holonomic constraints. We have written examples, we have discussed at length examples of non-holonomic, means holonomic constraints, and we discussed this non-holonomic constraints. Holonomic constraints. When we have discussed what is called as constraints, as I said, constraints are classified into two, holonomic and non-holonomic. Non-holonomic constraints are the constraints which cannot be expressed in the form of an equation. Non-holonomic constraints are the constraints which cannot be expressed in the form of equation. It can be expressed in the form of inequality or a condition. If any constraint which